Hello and welcome. In this video, we are going to start covering vector spaces. So in the book, there is section 2.4, vector spaces. Okay, so thus far, we have looked at systems of linear equations and how to solve them. We saw that systems of linear equations can be compactly represented using the matrix vector notation. So in the following, we will have a closer look at vector spaces, that is a structured space in which vectors live. Okay, so very important linear algebra concept. So let me continue reading the book. In the beginning of this chapter, we informally characterized vectors as objects that can be added together and multiplied by a scalar, and they remain objects of the same type. Now we are ready to formalize this, and we'll start by introducing the concept of a group, which is a set of elements and an operation defined on these elements that keeps some structure of the set intact. So 2.4.1 is this concept of groups, right? So traditionally this is covered under the subject abstract algebra, but groups are also useful in linear algebra. Okay, so let's see what groups are. Groups play an important role in computer science. Besides providing a fundamental framework for operations on sets, they are heavily used in cryptography, coding theory, and graphics. Okay, so the definition of a group is like this. So you consider a set G. So we start with a set and then they write this G in this kind of a form, G, this is an uppercase G, right, and an operation. Right, so there is a set G and an operation. This operation, an example like we know about addition, multiplication and so on, but this operation is abstract, right, abstract, and it's denoted like this, right? It's not multiplication or addition, it is a general abstract operation. So what it does is it takes elements from G cross G and then maps it to G, right, which is defined on G. Then so basically we have a set of elements and then we have an operation which is taking elements from G cross G, which is a cross product, which is it takes two elements from G and maps it to another element in G, right, which could be same or different or whatever, right, which is defined on, so this operation is defined on G, right. Then this regular G, uppercase G, which is defined as the set G along with this operation is called a group. So if the following hold, so the first one is what is known as closure. It's the closure of G, of the set G under this operation, right? So what does that mean? It means for every xy in G, right, they've written such that, so in the book generally it's written for every xy in G, you read it like for every x comma y in G, x and then this operation x and y, when they are operated by this operator, result in something, right, and that something which is an element in G also belongs to G. So that's the closure, right. So this is the first condition, closure of G under this operation, right. Actually that's a little bit surprising because here they have defined this operation itself as something that maps it to G. This looks redundant to me, but it's listed here, but it's okay. Second one is associativity.